Hi, and welcome to part two, naming acids and conjugate acids and conjugate bases. Just as before, you're going to need your notebook to copy down some notes. In this video, we're focusing on conjugate acids and bases. It's helpful to know the definition of acids and bases for this section, and also that ionization is the dissolution or dissolving of an acid base or even a salt where it forms its ions. Neutralization of an acid and base results in a salt in a water. So these pieces of background information are super helpful for understanding this. All right, let's talk about the definition of acids and bases. Acids are proton donors, or at least Brown-Stitt-Lowry acids are. They're proton donors, and they have a pH that's less than 7. We recognize them through their acidic proton, which is either the hydrogen found at the front of a chemical formula or at the end of a Q group. So when HF or CH3COOH ionizes in water, the things that it will form is the acidic proton H plus and the corresponding anion. Bases, on the other hand, are proton acceptors. So during a reaction, they gain protons. They have a pH that's greater than 7. And we recognize them as metal hydroxide or NH3. During ionization, the bases will break apart into the cation, which is usually a metal, and OH minus. And in the case of NH3, when it's put in water, it forms this NH4 plus, which breaks apart as OH minus and the ammonium cation NH4 plus. So those are the basics of understanding an acid, what an acid and a base are. And when we mix them together, neutralization reaction, they form a salt in a water. Okay, so now we're going to take some notes on the definition of conjugate acids and bases. So make sure your notebook or binder paper is ready. A conjugate acid is the acid form of a base when a base accepts a proton. And we'll see what that is in a moment. And a conjugate base is the base form of an acid when it donates a proton. So I want you to pause the video now to get these definitions down, and then we'll go through one example to get you a better sense of what this means. All right, so here we have a neutralization reaction. Magnesium hydroxide, which is our base, reacting with hydrochloric acid, HCl, and to form a water, and our salt here, magnesium chloride. So let's talk about what happens during this reaction. The base, and specifically the OH minus part, it's going to accept a proton, right? And it accepts it from the acid. And when it does, OH minus, when that accepts a proton, it's going to form water. So the base produces its conjugate acid, H2O. Notice that bases are on the reactant side and its conjugate acid will be on the product side. All right, let's look at the acid. The acid donates a proton, and when it donates a proton, it's going to form the Cl minus that is found in the magnesium chloride. So the acid, which again is on the reactant side, has a conjugate base, Cl minus, that's on the product side. So essentially the important pattern here is that the conjugates, whether they're acids or base, are found on the product side. And the way that you match them up is that a base on the reactant side, the thing that came from that base will be its conjugate acid. And for the conjugate base, that's what comes from the acid. So if you look on the product side, whatever came from the acid, it's going to be the conjugate base. All right, we're going to look at some more examples here. So I'm going to ask you to write down the conjugate acid or conjugate base for each of these species, and we'll go through them together. First one asks us to write down the conjugate acid of NH2CH3. This may look a little strange to you because you may not have seen something like this before, but actually you have. NH2CH3 is methylamine. This is very similar to ammonia, NH3. The only difference is that one of the hydrogens has been replaced with what's called a methyl group, the CH3 group. So during the reaction, the CH3 group does really nothing. It's just there to satisfy the bonding on the nitrogen. And these are the hydrogens that would do something during a reaction if something were to be done to them. So just note that this is just like NH3. You can just ignore this methyl group. All right, so if we're writing the conjugate acid of it, that must mean this is a base, because remember, bases produce conjugate acids. So bases are going to accept a proton. So what we're going to do to this is we're going to add a proton to it and see what we get. And that's what we do in this first example. So if we take NH2CH3, we're going to add a proton. And that proton is just going to change the number of hydrogens here, not on the methyl group. Do not touch this. So that's going to give us, it goes from H2 to H3. So we got NH3CH3. And then since we gained a positive charge on this species, since it's H+, it's going to be NH3CH3+. So don't forget the plus charge. Remember that in any reaction, number of atoms and charges should balance. So if you have a plus charge on this side, you should have a plus charge on that side. All right, let's do the conjugate base of H2O. So if this is a conjugate base that we're needing to write, that means that H2O is a acid, right? Because remember, acids are going to give you the conjugate base. So acids donate a proton, meaning we need to remove a proton from this to form its conjugate base. And that's what we do in this example. So if it's H2O, we're going to subtract from that a hydrogen. So that's going to give us one hydrogen now, and the oxygen comes along with. And since we're removing a positive charge, it's going to give us a negative charge. So we have HO minus, or OH minus, which is hydroxide. So the conjugate base of H2O is OH minus. All right, hopefully you have a better sense of this. So I'm going to ask you to do this one, and then I'll show you the work for it. Write the conjugate base of HF. All right, so if we're writing the conjugate base of it, that means that we need to remove a hydrogen. And when we remove an H+, that's going to give us F minus. So the conjugate base of HF is F minus. Last example, you're going to write the conjugate acid of NaOH. Now, remember, for these metal hydroxides, we're focusing on the OH minus part. That is the part that's really doing the work there. So I want you to you can ignore the sodium and just focus on the OH minus. If you want to write a conjugate acid of it, just like you did in the first example, add an H plus to just this section, to the OH minus section. Okay, so when you do that, if you add an H plus to OH minus, we're ignoring that sodium, we're going to get HOH, which is the same thing as H2O. All right, make sure you get these examples down, and then when you press play again, there'll be some practice problems for you to try on your own. All right, so here are some practice problems. You're going to write the conjugate acids or bases of the species described here. And when you are done, press play again and I'll reveal the answers. All right, so here are the answers. Check them as you go. And if you are confused about anything, just circle it and come back to it. I just want to note this color scheme is off. I usually make the conjugate acids pink here, and then this one should have been blue, but the work itself, what's written here, is correct. So in case you're confused about the coloring thing, this one should have been pink, this one should have been blue. Okay. Now we're going to do some examples where we're looking at neutralization reactions, and we've seen this early on. So you need to identify the conjugate acid and base pair from a neutralization reaction. And it's the same thing that we saw before. So the first thing that we want to do is we're going to identify the acid and base, and then we're going to figure out the conjugate acid and base from that. So this is our acid. It has a Cu group. And the thing that this acid produces or makes is going to be the CH3COO when it loses a proton. And so if this is the acid, that must be the conjugate base. And the base here is OH minus, and the conjugate acid of OH minus is H2O. So here we have that identified here, the conjugate base of this acid, and then the conjugate acid of this base. Again, for some reason my coloring scheme is off. I made a mistake on that. Finally, let's do it for H2O and H2O. Now, this is an ionization reaction. Remember ionization, when a little bit of water produces H3O plus and OH minus. So what is a conjugate acid and base? So one of these is an acid and one of these is a base. Doesn't matter which one you call it. But when H2O, if it acts as an acid, if it gains a proton, it's going to form H3O plus. If it acts as a base, it's going to gain a proton, forms H3O plus. And if it loses a proton, it's going to form OH minus. And so here we have our acid base, conjugate acid and conjugate base. All right, I want you to try some similar examples after you get this copied down. You're going to identify the conjugate acid and base pairs of these two reactions. And when you are done and you press play, the answers will be revealed to you. Okay, so here are the answers. For the first one, base is in H3, its conjugate acid is in H4 plus. The acid is H2O. H2O gives up a proton, form a conjugate base, OH minus. Next one, we have this acetate and we have this ammonium type thing here. So this is the base because it accepts the proton to form acetic acid, its conjugate acid. And this is the acid because it gives up one of its protons to form methylamine. All right, now that you have the basics of conjugate acid and bases, you're probably trying to figure out why are they important. In this unit, we're not going to really use them too much more, just other than identifying them. But later on in the year, they're important for what's called buffers. So buffers are made by a base and its conjugate acid, or an acid and its conjugate base. And if you mix particularly a weak acid and a weak base together, they form sort of a buffer solution. So if you take a weak acid and its conjugate base, you mix it together, they form a buffer solution. Or a weak base and its conjugate acid, it will form a buffer solution. Now, why are buffers important? Buffer solutions maintain a constant pH range. And a good example of that is blood. So your blood has a strict pH range of 7.35 to 7.45. If you go outside of that, you could die. In fact, you probably will die. So what keeps your blood within that strict pH, whether you're eating a bunch of acidic things or drinking a bunch of basic things, it's this buffer reaction here. All right, so this is the reaction that helps to maintain that. And when you learn more about equilibrium, you'll see why this sort of thing works, why buffers maintain a constant pH. But for now, just keep in the back of your mind that conjugate acid and base pairs are important for making buffer solutions, and that's why we're learning them now. All right, I hope you found this video helpful. And if you have any questions, talk to me next week. Have a quality weekend.